Hey, what's up, Algebra 2? It's Ryan. Today we're going to be talking about solving exponential and logarithmic equations. So in the last lecture about logarithms, which was a little bit lengthy, that's my bad, we talked about some of the properties of logarithms and how we can manipulate them, as well as just what logarithms are and how they're sort of the opposite of exponentials. And so today what we're going to be doing is using our knowledge of logarithms from our last lecture in conjunction with our knowledge of exponentials and using that to solve some exponential and logarithmic equations. And so we have a variety of examples from a bunch of different types of problems you might come across, not only in this Algebra 2 course, but also in SAT problems and math team problems. So let's just get started with some of these problems. Okay, so when we're solving exponential equations, we're really going to have two main cases. One when we have a common base, and one when we can't find a common base. What do we do when we have that sort of situation? So first, what do we do when we have a common base? So we're going to see this in our first problem, where we have 6 to the 2x minus 10 power equals 36. And so what this sort of situation entails is we see our bases, which in this case would be 6, and we see what that's equal to. So in this case, it's 36. And we say, can I rewrite 36 such that both sides of the equation have the same base? And so I know from my prior knowledge that 6 squared, or 6 to the second power, equals 36. So I can rewrite 36 as 6 squared. And now what this allows us to have is on both sides of the equation, we have bases of 6. And so we know that in order to keep that balance across that equal sign, we know the exponents must be equal to one another. So we can just drop the bases and set the exponents equal to one another. So we can say 2x minus 10 equals 2. And then from there, we have a pretty simple algebraic equation we can just solve. So we'd add 10 to both sides, we get 2x equals 12, divide by 2, and we get x equals 6. And it makes our life a lot easier. So in this third problem, we see that we have exponential expressions on both sides. And so we're going to talk about how we would go about that. And so we look at our bases. We have 8 and we have 32. And what we need to do to find a common base is think about, can I raise something to a power? And when that's something, that base, when we raise it to some power, I can get both 8 and 32. And so some of this requires some numerical fluency as well as just familiarity with exponents, and that comes with just doing a bunch of math all the time, or not all the time, but frequently. And so what I can do is when I see this, I can recognize that 2 to the third power is 8, and 2 to the fifth power is 32. So I can just sub those in for 8 and 32 and rewrite our equation. So in this case, I'd say 2 to the third 2 to the third to the 2x minus 1 power equals 2 to the fifth to the 2x plus 1 power. Okay, and this is the same as the equation above. We're just subbing in 8 and 32 for 2 to the third and 2 to the fifth, respectively. And now we have a common base of 2. So at this point, what we need to do is think back to our exponent rules. And so our exponent rules tell us that when we have a base raised to the m power raised to the n power, that's the same thing as that base raised to the m times n power. So essentially, when we have an exponent raised to another exponent, we can just multiply those. And so what we end up getting is 2 to the 3 times 2x minus 1 power equals 2 to the 5 times 2x plus 1 power. And we can just set those exponents equal to one another. So essentially, we get an equation that looks like this, where we have 3 times 2x plus 1 equals 2x minus 1. That's my bad. Sorry about that. And 5 times 2x plus 1. Okay? And then we just would want to distribute this 3 to get 6x minus 3, and distribute that 5 to get 10x plus 5. And then we'd subtract 10x from both sides to get negative 4x, add 3 to both sides to get 8, and then divide by negative 4 and end up getting x equals negative 2. Boom. Okay, so one thing I'll say is that from my experience, I see problems like this come up a lot on SAT tests. College Board seems to like them, and at least I'd say probably on every SAT I've taken, I've seen a problem that looks like this and uses this kind of approach. So it's good to put this in your back pocket because you might see it down the road on some SATs. Okay, so it's worth noting that not every exponential equation we're going to be able to find a common base. So we want to know what to do if we can't find a common base. So our first step is going to be to isolate the exponential expression. So in our first problem, where we have 4 to the x power minus 5 equals 9, what that would mean is adding 5 to both sides. So we get 4 to the x equals 14. And now 4 to the x, our exponential expression, is left by itself. And so then our next step would be to take the natural log of both sides. Now, it's also worth noting that you can take any log of both sides. You can take log base 10, log base 4, both sides. As long as you just do it to both sides, we want to maintain properties of equality. So whatever we do to one side, we have to do to the other. We just tend to do ln because that's the easiest. Or it's pretty easy, that or regular log. So in this case, we're going to just take the natural log of both sides. So we say ln of 4 to the x power equals ln of 14. Oops, my bad. I'm tripping. Okay, so now what we'd want to do is think back to that last lecture and some properties of logarithms, right? We have an exponent here, and when our argument has an exponent, we can take that exponent and put it out in front of our log. And so in this case, we can rewrite this as x times ln of 4 equals ln of 14, right? And now, by doing that, we can divide both sides by ln of 4 to isolate x. So we get x equals ln of 14 over ln of 4. And in this case, you'd get a calculator on this sort of test, and you'd say ln of 14, I'm getting 2.64, and ln of 4 is about 1.39. Just divide the two, and you end up getting 1.90. So we'd say x equals 1.90. Now, what we want to do in this case is plug that back in and check for extraneous solutions. So what I do, since we have our calculator, we just raise 4 to the 1.903 whatever power. And we get 14 minus 5 is 8.99999, which is just 9. So we know this works. We're good. Okay, so now let's do number 4. Okay, so we want to isolate our exponential expression, and so we want to subtract 2 from both sides. So we get e to the x plus 1 power equals 16 minus 2, which is 14. So now we want to take the natural log of both sides. So ln of e to the x plus 1 power equals ln of 14. And then we do what we did before, take that exponent of our argument and put it out in front. So I'm going to rewrite this as x plus 1 times ln of e equals ln of 14. Now, what is ln of e? Let's just think about it. Well, what is ln in the first place? That's log base e. We just write it as ln, the natural log. So log base e of e, that's essentially saying e to what power equals e. And so essentially all that's to say is ln of e equals 1 because e to the first power is e. So we can just rewrite this as x plus 1 equals ln of 14. And that's equal to x equals ln of 14 minus 1. All right, ln of 14 is about 2.64 like we said before. So minus 1 is going to be 1.64. So x equals 1.64. Perfect. And so you'll notice that it makes it easier that we use the natural log here when we have a base e. So sometimes what you'll see, and I don't mean to over-explain and possibly confuse you, but why some people might want to take log base 4 of a problem like this is by taking where we have our base, and that's equal to our argument, that would just simplify to 1. And so you can do that, and this would simplify to 1, and on this side we'd get log base 4 of 14. And so, I don't know, it's easier just using ln, and it's just simpler, and I probably shouldn't have explained that or digress, but it doesn't matter. Okay, so now let's go on to logarithmic equations. And so, before, right here, we used logs to sort of undo those exponents. Okay, and so when we're solving logarithmic equations, we might want to do the opposite and use exponentials to solve those. This is going to be sort of like our first case. So let's look at number 1, where we have log base 5 of 5x plus 9 equals log base 5 of 6x. And so this is sort of like our first case where we want our arguments to be equal to one another, right? To sort of maintain that balance on either side of that equal sign. So what we can do, just very simply, is rewrite this as 5x plus 9 equals 6x. 6x like that. And just solve like a normal algebraic equation. We subtract 5x from both sides, and we just get x equals 9. Okay, and sorry, I kind of switched sides on that. We'd get 9 equals x, but it's the same thing. And so here, what we want to do is we want to plug that in again and check for extraneous solutions. So when we plug 9 in, we get 9 times 5, 45, minus 9, 36, log base 5 of 36. And then we get log base 5 of 6 times 9. It's plus 9, my bad. I subtracted 9 before. So it's 9 times 5, 45, plus 9, 54. Log base 5 of 54 equals log base 5 of 6 times 9, which is 54. Sorry about that little mistake. So it lines up. We're all good. The main thing you want to look for in these sorts of cases is having an argument that's not positive. So that means equal to 0 or negative, because we can't ever have a negative or a argument that's 0 or negative. Because if we think about it, right, I'm not going to go in depth, but like an exponential might look something, like this, where theoretically we have an asymptote at 0, and so it never really touches 0, and it never really goes into the negatives. And so also if you think about it as, I'm kind of going here. If we say log base b of a equals k, we're saying b to what power equals a. And so we can't ever raise something to a power and get 0, right? That's not possible. And we also can't raise something to a power and get a negative number. We can get a fraction, right? If we have a negative exponent, we just take 1 over whatever that exponent is. And so we'd get a really small fraction, but we'd never get 0 or into the negative. So just remember, we can't have 0 or a negative argument. And the argument is what's inside this logarithm, right? Okay. So in this case, for number 2, we have this 2 outside. So we have 2 times log of x minus 3 equals log of 25. And so we're going to kind of do the opposite of what we did in the problems before. And since we have a constant we're multiplying on the outside of the logarithm, we can move that here and use it as our exponent. So we can rewrite this as log of x minus 3 squared. Remember that we're squaring the entire argument. So that means we're squaring all of x minus 3. And we're not just squaring x or 3, doing whatever. We actually have to FOIL. And then again, we use this one-to-one property that we were sort of talking about before, where we know the arguments have to be equal to one another if they have the same base. In this case, it's 10. It's invisible, but it's implied it's 10. So we can just say x minus 3 squared equals 25. And so in this case, you can go about this 2 ways. Let's actually just take the square root of both sides. So taking the square root of both sides, we'd get x minus 3 equals 5, as well as x minus 3 equals negative 5, right? We have to do that plus or minus since we're taking the square root of 25. And so we add 3 to both sides, we get x equals 8, as well as x equals negative 2. And in this case, we again want to remember to plug in our answer. So let's start with 8. So 2 times log of 8 minus 3. 8 minus 3 is 5. And all right, I'm just going to actually use this equation we have with 2 as our exponent because it's just easier. And so log of 5 squared, which is 25, equals log of 25. So we know 8 is good. And then in the second case, we'd have log of negative 2 minus 3, which is negative 5. Negative 5 squared, 25, equals log of 25. But let's actually think about this for a second. If I plug this into the original equation, I would have 2 times log of negative 2 minus 3. And so when we do negative 2 minus 3, that's going to give us a negative 5. And again, we have a negative number as our argument. And so we come across this problem where we have a negative argument, which we just talked about before, over here, where that isn't possible. So we know negative 2 is an extraneous solution. So in this case, we just say our answer is x equals 8. Right? You always want to be careful of that. Okay, so that's our first type when we have logs on both sides and they both have the same base. So we can just set the arguments equal to one another. But what if it's equal to a number? What can we do in that case? Well, we want to use just what we know about the relationships between logs and exponents. So in this case, right, we said that this is log base b of a equals k is just another way to say b to the k power equals a. So we're going to do that here. So we first want to condense and isolate each log, right? And in this case, it's already done for us. And we want to use this knowledge up here to help us in this case, right? So I can rewrite this as 2 to the 6th power equals x minus 4. So 2 to the 6, 6, my bad, equals x minus 4. What is 2 to the 6th? That's 64. So we'd say 64 equals x minus 4. Add 4 to both sides, and we get x equals 68. Perfect. And again, we'd want to plug this in. Sorry, I shouldn't have circled so soon. But we can plug it in. We can say 68 minus 4, what does that equal to? 64. And then we can, if we have a calculator, you may or may not have a calculator available to you. You can do log base 2 of 64, and you'd get 6. You can do that out in your calculator, or you can just sort of do what we did over here and say calculate 2 to the 6th and check if that equals 64. The main thing is we just want to make sure our arguments here are positive, right? They're not 0 or negative. Okay, so let's do problem 4. Actually, now we'll do problem 4, but in this case for problem 2, if you're doing that, just use some of your logarithm rules, right? Remember that we have the same base, it's both logs, so log base 10. And we can, if we're adding them, remember we can just multiply those arguments, and you can use that, and then you have one isolated log, and then you can solve from there. Okay, so let's do number 4, where we have log base 8 of x squared plus 15 equals 2. Okay, so again, we can just rewrite this as 8 to the 2nd power equals x squared plus 15. And this is also something to get used to, right? Just with logarithms. Thinking about, here's the thing, when I come across a logarithm, I kind of think about it like an exponential. I automatically go from this to that, just because it's easier for me to think about it in this term. I think it's just because that's the first thing I learned, so I always try to revert back to that. But yeah, here we just rewrite this log as an exponential. And we have 8 squared, which is equal to 64. And that's equal to x squared, sorry, my bad, x squared plus 15. Sorry, that's horrible. Plus 15. Here we subtract 15 from both sides. And we get 59/49 equals x squared. Take the square root of both sides to get x. And then we'd get x equals plus or minus 7, right? Remember that plus or minus. And so let's plug this back in, right? And we have to plug in both positive 7 and negative 7. So let's start with positive 7. So positive 7 squared is 49. 49 plus 15 is 64. And we know 8 squared equals 64, so we're good. All right, we have a positive argument. And then let's plug in negative 7. Negative 7 squared is, again, positive 49. 49 plus 15 is 64. 8 squared equals 64. We know we're good. Yeah, so since we have this squared, that sort of takes out whether this positive or negative even matters, because when we squared it's always going to be positive, so we know both are valid solutions. Okay, that's pretty much all of the examples I'm going to go over today. You do have this sheet where we go over, we just practice a bunch of different types of these problems and actually apply some of the concepts we talked about today. But yeah, if you come across a problem and you don't really know what to do, look back at this video, rewind, see how I solved some of these other problems, and use those strategies to help you in those problems. As always, if you have any questions, feel free to reach out. Stop me in the hallway, stop me in class, do whatever. I'm happy to help. Definitely go to your teacher, go to your peers who feel confident in this work. Definitely consult the internet, watch other YouTube videos, and yeah, go to a tutoring center. Use all the resources available to you so you make sure you have this information down. Okay, thank you for listening. I hope you have a good day.